Let us just wait for a few more minutes before starting the session to see if somebody else is joining.
Okay, sir.
So let us start today's session. Am I audible to everybody and is the screen visible?
Yes, sir.
Okay. So I welcome all of you to the 8th live session of the course Fundamentals of Manufacturing Processes being offered by Professor D.K. Dwivedi of IIT Roorkee. Uh, as in for myself, I am Abhik Dev, a PhD scholar in the Department of Mechanical Engineering at IIT Bangalore. And today we shall be discussing on the concepts related to the machining process, the fundamentals of the machining process, which is a metal removal process, or as you know, it is a subtractive process. Okay, so uh, uh, in this session we will discuss the basic the basic theory related to the tool used for machining process, and the chief formed, and the basic phenomenon involved in the machining, the material removal process, uh, and what are the factors that affect the tool life, and what are the different kinds of wear of the tool. So these are some of the concepts that related to which we will be discussing questions today. So at any point of time, if there is any doubt, you can ask. So without further delay, let us begin today's session. So you were asking HMT, as in heat and mass transfer, you were asking.
Yes, sir.
Uh, I'm not a TA for heat and any kind of heat transfer course this time, but yeah, like hopefully in the future maybe. Uh, why? Why did you ask about this?
सर आपकी स्क्रीन पे लिखा हुआ था हीट ट्रांसफर लैब डिपार्टमेंट ऑफ मैकेनिकल इंजीनियरिंग.
Oh, okay, okay. Yeah, my basically my research area is related to heat transfer in manufacturing processes. So I am working in a heat transfer lab. Anyway, so yeah, let us begin. So we will start with some very basic problems, and then we will go to some derivations and some numericals. So the first question is, the threading operation on the lathe machine is carried out using which of these? So can you give me the answer to this? That is the cutting of threads in lathe machine. Yes. So the cutting of threads is done using a single point cutting tool, and the lead screw of the lathe is utilized for this process. Okay, so the correct option is the single point cutting tool. The second question, the thickness of the chip produced by metal cutting operation like turning is which of these? Like in relation to the uncut depth of cut, that is uncut chip thickness. What is it? What is the relation of the thickness of the chip produced? So can you give me the answer to this? Can anybody give me the answer to this?
सर स्मॉलर देन द अनकट डेप्थ ऑफ कट.
Smaller than the depth of cut. Okay, that's your answer. Any other answer? Okay, somebody is asking to show the first slide. Don't worry, I think all of these resources will be made available to the group, so you can just focus on understanding as of now. uh, so I hope the first slide is clear. um, then we can, let's move to the second problem then. Yeah, so the thickness of the chip produced, somebody said it is smaller than the uncut chip thickness. Any other answer, or what is the reason that it is smaller? So this is the uncut chip thickness, and this is the chip thickness. Okay, this is the shear plane along which the shearing takes place. The chip is formed by the shear deformation of the material. So this is the shear plane of length ls. Okay, so we are asked to find whether t is greater than t naught, or t is less than t naught, or t is equal to t naught, or there is no relation between t and t naught. So uh, which one do you think is the correct answer? A. Yeah, so it is always greater than the uncut chip thickness. Why do you think this is the answer? Like, why will it be greater?
Sir, it depends on the thickness ratio.
Okay. Uh, it necessarily does not depend on the thickness ratio, but the thickness ratio actually depends on this value. Like what you were saying, it is a reverse of that. The thickness ratio will be a result of the thickness of the chip and the uncut chip thickness, not the other way around. So you see what happens in this case is, how does the deformation take place? So this is the shear plane, and this is the tool, okay, which is moving in this direction. So it does, the shearing does not happen like this. Okay, it does, the cut does not happen like this. Instead, the cut happens, if you observe it as a layer of stacks, then you will find that the shearing takes place like this. In minute layers you will find this. Okay, so this is how the shearing will happen in this direction. So on the application of shear force, what happens is that the grains tend to get elongated, or tends to get deformed uh, in a direction along the shear plane. As a result, from this side, a grain which is like this will start becoming elongated along the shear plane. Okay, as a result, the due to the elongation of the grains along in the direction of the shear plane, the thickness of the chip will increase as it crosses the shear plane. The thickness of the chip will increase because the grains will start getting elongated along the direction of the application of this shear force. And in this direction, since we measured the chip thickness is measured along this direction itself, so because of the elongation of the grains, there will be a increase in the length with respect to the uncut chip thickness. That is why we can say that the thickness of the chip produced is always greater than the uncut chip thickness. Okay, so is it clear to everybody?
Yes, sir.
Okay, so yeah, then if there is no doubt, then we will move on to the next problem. Okay, so the next problem is the stress on the cutting edge of a oblique cutting tool as compared to that of a orthogonal cutting tool for similar cutting conditions is always greater, always less, equal in most cases, or it cannot be
Yes, sir.
ascertained.
Always greater.
Always greater. So you are saying that the stress on the cutting edge of an oblique tool is always greater, right?
Yes, sir.
Why so?
Sir, sir, according to their geometry,
Yes. So what happens according, like what happens in the in that, like according to the geometry, what do you find?
sir, in orthogonal cutting, the cutting tool and the workpiece is perpendicular to each other at 90 degree.
Yes.
But in oblique cutting, there may be some inclined.
Yes.
That's why.
Okay. So yeah, so this requires a bit of clarification actually. uh, so just pay attention here. So see, mm, this is the orthogonal cutting, right? And this is the oblique cutting. Okay. So in this, this is the contact area. This much is the contact area. Whereas in this is the contact area. So for the same depth of cut, can you tell me the contact area will be more in oblique cutting or orthogonal cutting?
Sir, in oblique cutting.
Yes. So for the same cutting conditions, which means the same cutting force is also applied. Okay, so for the same cutting force and same depth of cut, uh, so since the area is more in case of oblique cutting, then the stress will be more in which one? Remember, the stress, the stress, if we say stress is force per unit area. Okay, so the force is same, cutting force is same, area is more in which one, oblique cutting or orthogonal cutting?
Oblique cutting.
Yes. So area in the oblique cutting is more than the area in orthogonal cutting. Cutting force is same. Then from this ratio, can you tell me which one will have a greater value of stress?
Oblique.
Oblique cutting. You tell me, if the denominator is larger, then this value will be, suppose force is 100 and area is, for orthogonal cutting it is 5 mm. Okay, then the stress value will be what for orthogonal cutting? 20.
20.
Then same for oblique cutting, the force value is 100, cutting force is same, and the area value is, say it is more than 5, obviously, let us say 10, whatever it is, then what will be the stress?
10.
Then which one will have a higher stress?
Orthogonal.
Yes. So the stress in the orthogonal cutting is always more than in oblique cutting for the same cutting conditions. Okay. So is it clear? to everybody?
Yes, sir.
Is there any doubt? Also, I would like to mention here that since the area of contact between the tool and the workpiece is more in case of oblique cutting, so the heat transmission, the transmission of heat, just a minute. Yes. Yes. So the transmission of heat between the tool and the workpiece in case of oblique cutting will be more. So in case of orthogonal cutting, the heat will be localized at this region. Okay, the heat will be localized in a small region. But in oblique cutting, since the area is more, the heat transfer will be more. That is, the heat will be easily dissipated from the tool to the workpiece or vice versa. That is why the tool life will be greater in case of oblique cutting as compared to orthogonal cutting for the same cutting conditions. Okay, so any doubt in this?
No, sir.
Okay, now the next question. So in the machining operation, the secondary shear occurs at which of these?
सर प्रीवियस स्लाइड एक दिखा दीजिए. सर इसका आंसर बी हो जाएगा ना फिर अब.
Huh?
सर इसका आंसर बी होगा ना अब.
Stress in the ortho. Oh, huh. Stress in the oblique cutting. Sorry. Stress in the oblique cutting is always lesser. Yeah. Stress in the, yeah. So the opposite of this, yeah. The stress in the oblique is always lesser than stress in the ortho. Thanks. Yeah. So the next question. So can you give anyone give me the answer to this? In machining operation, the secondary shear occurs in which of these? So yeah, can anybody give me the answer? So do you know where the secondary shear occurs or what is secondary shear? Anybody?
Yes, sir.
So where does the secondary shear occur?
Sir, secondary shear occurs between the metal chip and the cutting tool.
Yes, yes, exactly. What is the reason for the secondary shear?
Heat generated or friction,
Yes.
plastic formation.
So as the chip moves along the workpiece, there is a high temperature plus friction. Due to this, there will be a secondary deformation, shearing deformation occurring in this region, which is termed as secondary shear. So the secondary shear occurs at the tool chip interface. Okay. So the answer is option number D. Okay. So coming to the next problem, discontinuous chips are formed when, like, which of these conditions result in the formation of discontinuous
Sir,
chips?
hard and brittle materials.
Okay. Any other option?
Sir, I think all of the above.
Yes, exactly. So all of the above results in the discontinuous chips. So discontinuous chips are formed when brittle material, then there is low cutting speed, high feed, and high depth of cut. Okay, and also if there is a high cheap tool interface friction. So in these conditions, discontinuous chips are formed. So the correct option is option number D. Uh, so I request all of you to interact and try to give the answers. Then only we will be able to hold an interactive session. If you do not give an answer, I will not be able to clear the doubts. So I request all of you to give answers or try to give the answers. Uh, so coming to the next problem, in machining operation at low speed, most of the heat goes to which of these, like tool, chip, and workpiece. So that whatever heat is generated in the machining process is going either to the tool or to the workpiece, that is the cut workpiece or machined workpiece, and the chip. So at low speed, most of the heat goes to which of these, and at high speed, most of the heat goes to which of these. So, which one will be the correct answer? Start with at low speed. So, at low speed, what happens? Any idea? Anybody, just whatever you think, you can give an answer. So, you were saying that at low speed, most of the heat goes to the discontinuous chip or the chip. Okay. Any other answer?
Sir, I think chip tool and tool.
Which one? Sorry.
Option D.
Option D. Chip and tool. Okay. So, see, suppose this is the cutting speed, okay, and this is the heat generation, and this is the 100% dissipation, 100% heat dissipation, okay, and this is 50% heat dissipation. So there is a graph which becomes like this, and something like this. Okay, so in this graph there are three sections. Say this is 1 and this is 2. Then at any value of the cutting speed, the region below the curve 1 will give the fraction of the total heat that is dissipated in the chip. The region between these two, 1 and 2, will give the fraction of heat dissipated with the workpiece, and the region above 2 will give the fraction of heat dissipated with the tool. So at low cutting speed, see, very less, if we take a speed value here, then very less heat is dissipated in the chip and maximum heat is dissipated in the tool. Okay. uh, and at higher value of the cutting speeds, if we take a cutting speed very high, then maximum heat is dissipated in the chip and very less heat is dissipated in the tool. Okay, so at very low cutting speed, most of the heat will be dissipated in which one now? This is an experimentally observed uh, you know curve. So this is what practically happens. So at low cutting speed, in which one tool chip or the workpiece will the maximum heat will be dissipated? You look at this region. So at low cutting speed, this is the fraction, like this is in 10, around 10%, and in the chip, in the workpiece, it is from say 10% to 40%, that is 30%, and from 40% to 100% is in tool. So which one, the most of the heat is going into which one? At low cutting speed, this is the amount of heat going to the chip, this is the amount of heat going to the workpiece, and this is the amount of heat going to the tool. So uh, at low cutting speed, this one low cutting speed, which one is carrying the maximum heat?
Workpiece, sir.
Workpiece. How is it workpiece if suppose this is 10%, this is, you see, for less than 50%, then it is 40%, then what is the amount of heat carried by the workpiece? See,
Sir,
10% of
50, sir, 50 or above.
see, the chip is carrying this 10% of the heat, the workpiece in this region is carrying 40 minus 10, that is 30% heat, and the tool is carrying 100 minus 40, that is 60% of the heat. So which one is carrying the maximum? The tool is carrying the maximum heat. How is it the workpiece, like or how is it the workpiece is carrying more than 50%? The workpiece is carrying, see, this region, this is the heat carried by chip, this region is the heat carried by workpiece, and this is the heat carried by tool. So what is the heat carried by the chip in this case? Tell me, anybody, just tell me. If this is 10%, then what is the heat carried by the chip?
So 30.
Why are you subtracting 40 minus 10? I am telling you, from this fraction, this value, suppose this is a curve and this value is given as 10, and this is the amount of percentage of heat that is being carried away by 1, by a value a, this is value b, and this is value c. Then this value a will be what? If this is 10%, this is 40, just take it as a linear scale, and this is 100. Then this value, if this is 10 and this is 0, then what is the value of a?
10.
Yes. What is the value of b?
30,
Yes, 30. And what is the value of C?
60,
Yes. So what is the here? Can you now tell me what is the heat carried by the chip?
10%,
Yes, heat carried by the chip is 10%. What is the heat carried by the workpiece?
30%,
Yes. And what is the heat carried by the tool?
60%.
60%. Okay. Now, at higher cutting speeds, suppose in this region, so this is say 80, this is 90, and this is 100. Now, what is the heat carried by the chip?
80%,
Yes. And heat carried by workpiece?
90%.
90. 90. Is it
Sir,
90?
10%,
Yes, 10%. And what is the heat carried by the work tool?
10%.
Yeah. So did you understand how to go about this?
Yes, sir.
Hmm. So now tell me, so at low cutting speed, which one will carry the maximum heat? The green one is the low cutting speed region, right? So which one is the low, which carries the maximum heat?
Sir, at low speed, maximum. Sir, at low speed, the maximum heat goes to the tool.
Yes, and tool carries maximum heat. And at high cutting speed, what happens?
Chip.
Yes, chip carries maximum heat. Okay, so the correct answer,
Option C.
yes. So the correct answer is option number. So is it clear to everybody? If there is any doubt for anybody, you can ask. If there is any doubt to anybody, because most of the people were confused. So if there is any doubt till now, you can ask. So should I take that if it is clear to everybody?
Yes, sir.
Okay. Then I'm moving to the next problem. Please do not feel scared or like shy to ask. Okay, it is perfectly clear if it is not like totally understandable to you. So you can ask. During machining operation, tool chip interface temperature can be lowered by increasing the value of each of these. Can anybody give me an answer to this? Anybody? Any guesses? Any guesses? So what do you think will increase with the increasing cutting speed?
Sir, generally, the tool chip interface temperature increases with increasing in cutting speed of feed or depth of cut.
Yes, you
But
are correct. So with the increase in the cutting speed, the tool chip interface temperature will increase. With the increase in the uncut chip thickness, that is the depth of cut. So with the increase in the depth of cut also, the tool chip interface temperature will increase. What about the specific energy? That is the energy consumption per unit volume of the material removed. So what happens if we increase that? That means that more energy is required for the cutting, and hence since we are supplying more energy, there is a chance that the tool chip interface temperature will also increase, though in most of the cases it cannot be directly ascertained. But what is thermal diffusivity of the tool or the chip? So thermal diffusivity implies thermal diffusivity is the ratio of heat conducted to heat stored. Okay, so as thermal conductivity, that is alpha, increases, okay, heat conducted increases, heat conducted or we can say this one, heat conducted increases. So heat conducted increases. So as heat conducted increases, so the temperature will increase when the heat is being stored. But as heat is conducted, that it is heat is being dissipated away. So the tool chip interface temperature will have a chance of getting lowered. So the temperature at tool chip interface decreases. Okay, so is it clear?
Yes, sir.
Okay, now coming to the next problem.
Sir, thermal diffusibility was the answer.
Yes, the correct answer is thermal diffusivity. So crater wear in tools occurs because of the rubbing between which of these? Can anybody give me the answer to this? C, tool and the chips. Yes, this is the correct answer. So what happens is that when when the chip flows like this, okay, due to friction in this region, there is a continuous rubbing action of chip on tool rake surface. As a result, the tool has a wearing like this. Suppose this was the initial tool geometry, so it will become like this crater, small craters will be formed like this. Okay, so this is called the crater wear. So the correct option is option number C. Okay, is it clear? There is another kind of wear. So supposedly from the top view, if we see, this is the end cutting edge and this is the side cutting edge, and the material is in contact, this side is in contact with the workpiece. So this is the workpiece. Then there will be a wear on the flank, gradual wear on the flank. due to interaction of the workpiece with the flank or, with the side cutting edge or the flank surface. This is called the flank wear. This is done the machined workpiece. This is due to the rubbing with machined workpiece. Okay, so is it clear to you?
Yes, sir.
Okay. Okay. Now, to avoid the rubbing of the machine surface with the flank of the tool, the angle given to the tool is which of these? So, to avoid the rubbing of the machine surface with the flank of the tool, the angle given to the tool is which of these? Can anybody give me the answer, please?
Sir, clearance angle.
Yes. So, the correct one is the clearance angle. Okay. So, this angle, this is the chip form. This is the machined surface. Okay. And to avoid contact of this flank region, this is the flank region with the machine surface, we give this angle which is called the clearance angle. So answer is option number B. Now, the next question, so the tool signature is which one of these? So can you tell me what is tool signature? Before going to the order, what is tool signature? Can you tell me?
Sir, tool signature are the various features of the cutting tool, like
Features,
ASA tool signature, ORS tool signature.
but what do they contain? Like what do they consist of? What features do we specify in a tool signature?
Sir, like what will be the nose radius? What will be the back rack angle, cutting edge angle, like this?
Yes, so how many features are specified?
7.
Yes, 7 features. So now can you tell me which one will be the correct order of tool signature here? Anybody?
Sir, I think answer A.
Yes, sir. Option A is correct. I think ASA tool signature is there in option A.
Okay. Well, mm, so before we go into this, let me give an idea about the various angles so that it becomes clear to everybody. So this is a basic uh, representation or schematic representation of a single point cutting tool. Now, can you tell me the various angles here? And just let me start pointing out so that you can see. So can you tell me which angle is this? Or let me begin with the sides. So which side is this? What is this? What is this called?
Side cutting edge angle.
This is the side cutting edge, not the angle I am referring to. Side cutting edge. We are starting with the edges, and which one will be this? This is,
End cutting edge.
yes, end cutting edge. What is this face called? This face?
Back rack angle.
Again, I am asking about the face, not the angle. So what face? This is the rake face, right?
Okay.
Yeah. And what face is this one?
Flank.
Yes, correct. So this is the flank. And what is this?
Which one?
This the area that I am marking.
Notch radius.
Yes. So this is the nose radius. Now the basic things are clear. Now we will go into the angles. So what is this angle?
Relief angle, side relief angle.
Yes, so side relief angle. So side relief angle. So side relief angle is basically the angle that the flank or the flank, see the flank contains the side cutting edge. Okay, hence the name side is coming with the relief angle. It is basically a relief angle in which the side cutting edge is coming into picture, and the flank contains the side cutting edge. So the angle made by the flank with the vertical direction, with this direction, is called the side relief angle, which is denoted by say CS. Okay, and what is this angle? What is this angle? Yes, so this is the, yeah, please tell me. If somebody wants to say, please tell me.
Sir, I think clearance angle.
No, so this is not the clearance. Clearance is given to the flank surface. Okay, this is this side, uh, this is the
Side
side cut.
relief angle. Side
Yeah,
relief.
yeah. So the side cutting edge, it comes in contact with the workpiece. So for the gradual contact with the workpiece, we provide this angle, which is called a side cutting edge angle. Okay, which is denoted as say psi s. Now, what is this called? The angle made
Side
by,
relief angle.
yes, the angle made by the face, the flank face contain not the flank face, the face which contains the end cutting edge with the vertical is called the end relief angle or end clearance angle, which is denoted by CE. And just sorry, yeah. So this angle is called what?
End cutting edge angle.
Yes,
And cutting edge angle.
yes. So this is the end cutting edge angle. Now, before we go further, let me ask you the views. So if we view this tool in a side view, that is from this side, from the flank surface, if we are viewing it, like from this side we are viewing it, okay, from this side we are viewing it. Okay, then what do we see? If we see in the side view, then what will we observe? We'll observe a tool section like this. So what is this angle?
Back rack angle.
Back rectangle.
Yeah, so this is the back rake angle, alpha. Okay, and what is this?
Clearance angle.
Yes, which clearance angle?
Front.
End relief. End.
End. Yeah, end clearance angle. See this angle. This is the angle that we are seeing. If we see from this side, we will see this angle, right? This angle we will see. So this is the end relief angle. Now if we see in the front view, okay, front view as in from the this side, if we observe from this side, then what are the angles that we will see? We will see a section like this. Okay, so what is this angle and this angle? What is this angle?
Rack angle.
This is the side rake angle.
Side rectangle. Side rectangle.
Okay, side rake angle. Let's denote it to beta. And what is this angle? You check from the diagram. Which angle we will see here?
Side relief angle.
Yes, so side relief angle. And now comes the top view. So in top view, we will see something like this. So what is this angle and what is this angle?
Side cutting edge angle.
Yeah, so this is the side cutting edge angle and this is the end cutting edge angle.
End cutting edge angle.
Okay, now remember, now if we come to the tool signature, first,
And also nose radius will be there in top view.
yeah, this section, the nose radius will be there. Yeah, so when we specify the tool signature, we will move first with rake angles, back and side. Then we will move to clearance angle, end and side. Then we will move to cutting angles, end and side, and then we will go to radius. First, we will see rake angles. Okay, first are rake angle. Let us just write rake angles. We will write the end and the side later. Okay, now clearance angle, clearance angle, and clearance angle. Then we will go to cutting angle and cutting angle, and then we will go to radius. So before we go, what are the exact like specifications? You will remember. You have to remember. It is always specified as end first, then side. End first, then side. End first, then side. Okay. So there is no end rake angle. But see, the rake angle associated with the, when we see the back rake, this is basically the end cutting edge. So the inclination of the end cutting edge from the horizontal is basically giving the back rake angle. Okay, so this the back rake angle is basically associated with the end cutting edge. Okay, so what did I say? End first, then side. So it will be first back rake angle, then side, end first, then side. So end clearance angle, then side clearance angle. End first, then side. End cutting edge angle, and then side cutting edge angle. And then is the radius. So the option B. So the correct option is option number B. So what do we have to remember here? First rake angle, then clearance angle, then cutting angle. Rake angle, clearance angle, cutting angle. End first, then side. So so the way to remember it you have understood?
Yes, sir.
Yeah. Okay. So is there any doubt in this? Anybody? If there is any doubt, you can ask. Okay. So I'm taking that there is no doubt. So going to the next problem. So we have to find the relationship between the shear angle, the chip thickness ratio, and the rake angle for the machining operation. Okay. So what is the shear angle? What,
Phi.
yes. What is the chip thickness ratio?
R.
And what is the rake angle?
Alpha.
Okay. So if we have a schematic of the diagram, that is the machining operation here, okay, then which one will be the rake angle? Which one will be the rake angle? Can you tell me? Tell me. Yeah, any idea?
सर रैक एंगल सर जहाँ पे डॉटेड लाइंस हैं वहाँ पर
वहां पे किसके साथ? डॉटेड लाइंस विथ विच वन?
सर टूल और चिप
Yeah. So this is the rake angle. What is the shear angle? Which one?
सर वर्क पीस एंड चिप के बीच में शेयर एंगल
Okay. Yeah. So this is the shear plane angle. This is the uncut chip thickness, and this is the cut chip thickness. So T is basically uncut chip thickness by chip thickness, which is essentially less than 1. Now, can you tell me how to go about this? How do we proceed for the finding the relationship? What is the basic equation? Okay. So yeah. So tell me, in this is drawn here. Okay, this region has been drawn here. Now, in this small right angle triangle, okay, this is the right angle here. So tell me, sorry, just a minute. Yes. So this is the right angle. Okay. So if this angle is alpha, what is this angle? What is this angle? The sum of the three. What is the value of the sum of the three angles in a triangle?
180 degree.
So one angle is 90 degrees. So what is the sum of the other two angles?
Ninety minus alpha.
Yeah. So this angle will be 90 minus alpha. Okay. So sorry, there is a mistake. This is not alpha. This is phi. Okay. So just a minute.
फिर इसमें हम साइन रूल लगाएंगे.
Sine rule. We will use the sine rule itself, but we have to find the angle. So see, mm, let me redraw the diagram in a bigger way. This small diagram is creating a bit of confusion. Okay, so this angle is phi. This is T naught. This is TC. Okay, and this angle is alpha. Okay, so if this angle is alpha, then just a minute. Uh, just a minute. I will be back. Yeah, sorry about that. So suppose we draw a line parallel to this here. So what will be this angle? This angle will be equal to phi. How? These are alternate angles. So alternate angles are equal. Now, as we have seen previously, if this angle is a alpha, then this angle, this small angle will be, as we have seen previously, 90 minus alpha, since this is 90 degree. Then these are also vertically opposite angles. So vertically opposite angles are equal. So this angle will be 90 minus alpha. So this is 90 minus alpha. This is 90. So this angle will be alpha. Okay. So this angle is phi and this angle is alpha. Hence, this angle will be phi minus alpha. Okay. So have you understood how we get this value phi minus alpha, this angle?
Yes, sir.
Is it clear to everybody? I want everybody to understand how this has been phi minus alpha. So yeah, so is it clear to everybody?
Yes, sir.
Okay. So what after getting the angles, what do we get the final diagram to be? Okay, this is 90, this is 90, this is T naught, this is T C, this is LS, this is phi, and this is phi minus alpha. Okay, so if we write T naught in terms of LS, what we get? T naught is LS sine phi. Okay, and what is TC? TC is LS cos phi. From here we can write LS is T naught by sine phi, and from here we can write LS is TC by cos, sorry, phi minus alpha. Phi minus alpha. Okay, therefore since LS is same, so T naught by sine phi is equal to TC by cos phi minus alpha. If we had used the other angle like this one, this angle will be 90 minus phi minus alpha. Okay, so if we had used the uh, sine rule, this would be sine of 90 minus phi minus alpha, and hence it will come as cos of phi minus alpha, and hence that is how the sine rule can also be used. So T naught by Tc is equal to sine phi by cos of phi minus alpha. So T naught by Tc is equal to R. So this is the relationship between the chip thickness ratio, the shear angle, and the rake angle. We can further simplify this to find the shear angle. How to do so? See, we have got R is equal to sin phi by cos of phi minus alpha. So let us take a reciprocal of this. So cos phi minus alpha by sin phi. This is cos phi cos alpha plus sin phi sin alpha by sin phi. So it comes to be cos alpha by tan phi plus sin alpha. This is 1 upon r. So now we are multiplying it again. So 1 is equal to r cos alpha by tan phi plus r sin alpha. So r cos alpha by tan phi. This is equal to 1 minus r sin alpha. If we take now tan phi, so tan phi will be equal to r cos alpha by 1 minus r sin alpha. So this is another relation where if we know the chip thickness ratio and the rake angle, so the rake angle is a tool specified thing, okay, and the chip thickness ratio is determined from the depth of cut that we are giving. Okay, so these two values will be known. So from that we can determine at what angle the shearing will take place. Okay, so that is how we get the value of the shear plane angle. Okay, so is it clear to you?
Yes, sir.
Okay, now coming to the next problem. Determine the value of the shear strain in machining operation in terms of the rake angle and the shear angle. So how to go about this? So what is basically shear strain? The basic definition of shear strain, can you tell me? What is the basic definition of shear strain? Anybody? Can anybody just tell me what is the definition of shear strain, like in strength
Sir,
of
I
machining?
know the formula.
Yeah, sorry.
I know the formula that how to calculate shear strain, but I don't know the definition.
What formula do you exactly know?
Sir, cot phi plus tan phi minus alpha.
No, that is the that is the value of the shear strain in the machining operation. I am asking what is the definition of a shear strain? What is the value of shear strain? Like, sorry, not what is the value. What is the basic definition of shear strain? Like in which is applicable to anything, like in fluid, in strength of materials, in any general definition of shear strain. Because if you don't know the general definition of shear strain, you won't be able to determine what is the shear strain in machining.
Sir,
Yes, yes.
basic definition of strain is change in length upon original length in
Yeah,
terms of
yeah, so that is the definition of basically linear strain. So what is the definition of shear strain? So shear strain is basically the change in the angle between two initially perpendicular lines. Okay, I don't know if you have seen this diagram or not, but suppose this is an element which has got deformed like this, which was initially perpendicular. Okay, this is the action of the shear. Okay, then the angle shear strain will be the value alpha. That is, initially they were perpendicular, now the angle has become alpha. Okay, so the change in the angle uh, between two initially mutually perpendicular lines. So initially it was this, now the angle has become alpha between two mutually perpendicular lines. The change in the angle has changed by the value alpha, so the shear strain is alpha. Okay, this is the definition, that is the change in angle between any two mutually perpendicular lines. So this is the basic definition which is applicable everywhere, general case. Here it is alpha. Now for very small angles, alpha becomes equal to tan alpha. Okay, like for suppose 1 degree, tan 1 degree is equal to nearly equal to the value 1 or something like that, or even lower. Suppose if it is 0.5, then tan of 0.5 degree will be close to 0.5. So that is for very small angles, tan the value alpha will be equal to tan alpha. Now with this approximation we can say that tan alpha, let us name this, suppose A, this is B, this is C, this is D, and this is B dash. So tan of this alpha will be B into B dash, B to B dash by AB. That is shear, if we consider the deformation in terms of deformation, then this is shear deformation by this length AB. So here it is the thickness between the planes. Thickness between planes. Okay. Now we will apply this concept to the shear deformation in machining operation. So as I have previously said, how does the deformation happen? Deformation happens as stacks like this. Okay. So what will be the initial length, that is the thickness between the planes initially? So these two planes, suppose we are considering, then the thickness between these two planes, suppose these two planes, the thickness between these two planes, let us say this thickness is delta H. So this thickness between the planes, the perpendicular thickness, okay, it has to be perpendicular, is the thickness AB. And what is the deformation due to shear? Which one is the deformation due to shear? See, this point was supposed to be here, but due to the deformation, this point has got shifted to here. So what is the shear deformation? So shear deformation will be from here to here. Let it be delta S. Okay. Is it clear till now? If it is not clear, please ask. Because if it is not clear now, then the rest of the derivation will be difficult. Yes. Anybody? Is it clear to everybody?
Yes, sir.
Eh, everybody else? Is it clear to you? This is the shear and this is the initial thickness between the planes. Yeah, please, if it is clear, just let me know. Otherwise, I cannot proceed. To everybody. Okay. So I am getting thumbs up from two people. The other two people are not responding.
सर डेल्टा एच एंड डेल्टा एस समझ में नहीं आ रहा है कैसे लिया.
Okay. So see. So the deformation starts from here. Okay. These planes are parallel like this. These are parallel planes. Okay. Because of the action of the tool, what happens is this point, it was like this, something like this, a plane like this. Okay. So this point now gets shifted here because of the shear force by the tool in this direction. The point gets shifted here. There is a shear deformation. This one. So this point which was supposed to be here gets shifted here. That is why there is a shear. Say the planes without shear would have moved like this. without shear, okay, these planes would have been like this, like this, like this, okay, would have moved like this if there is no shear. Okay, now which, because of the shear, this point, okay, this point will move to a point here like this because of the shear force. So this plane was, this point is still here, so there will be a shear, resulting shear displacement in this direction, that is the plane will get shifted like this because of the shear. You compare with this one, if we take this one, you take and you compare with the red diagram in a form like this. Suppose this is A, okay, this is B, this is B dash, this is C, and this is D. Okay, now you tell me which one will be the shear. If we compare with this one, what will be the shear? This is the same diagram. A, B, B dash, C, and D is shown here. A, B, B dash, C, and D. It was initially B, A, B, C, D, but due to shear, B has become B dash and C has become C dash, or C has become, say, C dash. C has become C dash. So what is the shear as compared to this angle? If we say, so what will be the shear? So the shear strain will be this region, right? This region, that is B, B dash by this region AB. Remember, this is perpendicular length. AB is the perpendicular length. It has to be the perpendicular length because it was initially mutually perpendicular lines. Now BB dash we have taken as delta S and AB we have taken as delta H. Just arbitrary values we have taken. We have just used the delta S and delta H for denoting these values. If we do not denote also, it is fine. We will just find out the values. These are not any particular values. We have just denoted it.
Okay, sir, I understood.
Okay. So yeah. Now we will go to the next part, like how to go about this. So if we enlarge this triangle, see, this is a triangle. Okay, so this triangle, if we enlarge, okay, then we will get something like this. Okay, where this is phi, this value, let us denote it like as A, this is B, this is B dash. Okay, and suppose we draw a perpendicular here and we denote it as O. Okay, so the length OA, that is the perpendicular length, is delta H, and the length B to B dash is the delta S value. Now this angle is phi, so this angle will also be phi. This is the rake angle, right? Alpha. So if this is the rake angle, this angle, alternate angles, this will also be alpha. Okay, so see, this angle is phi, this angle is 90, so this angle will be 90 minus phi. Okay, again this angle is alpha, this angle, this total angle B dash A, and say this is B, this angle is 90, this angle is alpha, so this angle will be 90 minus alpha. Okay, so this angle will be what? This angle will be 90 minus alpha minus 90 minus phi. that is, sorry, 90 minus alpha, 90 minus phi. So this angle will be phi minus alpha. So this angle is equal to phi minus alpha. Okay. So is it clear till now? This angle calculation, is it clear? And if there is any doubt, you can tell me, like, where is the doubt, which angle you are not able to understand, and I will explain again. Yeah, please tell me. Is it clear or is there any doubt? And if there is any doubt, then which part do you have a doubt? See, if you want me to repeat, you can also ask me to repeat. So please tell me. Yeah, anybody, please tell me. Otherwise, I will not be able to proceed, right? I have to know that you have understood till now. You can just unmute and tell me if you have understood.
Yes, sir.
So the others,
Okay, sir, understand.
okay. So, mm, yeah. So this is the angles. Now the shear strain, say gamma, it is equal to delta, what we have seen, delta S by delta H. That is the shear deformation by the original distance between the planes. What is delta S? Delta S is BB dash by delta H is OA. What is BB dash? BB dash is OB dash plus OB by OA. Now OB dash by plus by OA, it can be written as OB dash by OA plus OB by OA. Now in this triangle, see OB dash by OA. What is this? What is tan phi? See, tan phi is equal to OA by OB dash. From this triangle, if we see triangle, from triangle OAB dash, tan phi is equal to OA by OB dash. Therefore, cot phi is equal to OB dash by OA, right? So this is equal to cot phi plus now OB by OA. OB by OA. This angle is phi minus alpha. So in triangle OAB, tan of phi minus alpha is equal to OB by OA. Okay, so OB by OA is equal to tan of phi minus alpha. So this is the derivation for the shear strain, the formula that you were saying. So is it clear to everybody now?
Yes, sir.
And yeah, please.
Yes, sir.
Yeah, okay. So I request all of you to please just do not try to memorize the formula. You try to understand the how this is derived, so that like even if you forget the formula, you will be able to derive it. Okay, so coming to the next question, so chips with built up edges are formed for which of these? So what are the chips with built up edges? What are chips with built up edges? Anybody? The basic idea of a built up edge chip.
Sir, when the material deposit on the chip uh, while removing the material,
Okay, which material deposits on the chip?
remove the material.
Okay, okay. So the idea is okay, but it needs a bit of clarification. So what happens is that when the chip is being removed, okay, there is a chance that there is a chance that the material that is being removed is partly getting cold welded. That is, at low temperature, it is joining with the tool surface like this. Okay, this is called a built up edge. Since this is cold welded, as the chip continues moving over this, as the chip continues moving over this built up edge, due to friction, it will keep on applying force on the built up edge, and there will be a time when this chip will take away this built up edge along with it. That chip is called chips with built up edges. Okay, chips carry
Yes, sir.
away the broken built up edge. It's called chips with built up edge. Now, when the chip takes away the built up edge, a fraction of the tool material may also be removed. So it decreases the tool life. Now, when is this? The question is, when is this cold welding possible? So, for brittle work material, is it possible for brittle work material?
No, sir.
Why no?
Sir, sir, because in brittle workpiece material there will be discontinuous chip.
Yes, brittle materials, the chips will be discontinuous. So they won't be able to take away this built up edges. Now, high cutting speed and high feed. So what should be the value of the cutting speed for cold welding?
Sir, option C is correct.
Yes, option C is correct. So the cutting speed should be low. So the temperature should not be so very high. Okay. So the temperature should not be very high. With the increasing in cutting speed, we will see that the temperature is also increasing. So the temperature should not be very high. So the cutting speed should be low and the feed should be high. Okay, feed should be high so that the material that is to be removed is like there is a accumulation of some fraction of the material. That is how the built up edge will be forming. So the correct option will be option number C. Okay, now coming to the next problem, it is a numerical problem. So in a machining operation involving single point cutting tool, the rake angle is given as 10 degree. The uncut chip thickness is 5 millimeter and the cut chip thickness is 8 millimeter. If the width of the workpiece is 10 millimeter and the shear strength of the workpiece material is 40 megapascal, determine the cutting force, sorry, not the cutting force, the shearing force in kilonewton required. So what all data are given? The rake angle alpha is given as 10 degree. The uncut chip thickness, or sorry, T naught, it is given as 5 mm. The cut chip thickness is given as 8 mm. The width of the workpiece is given as 10 mm. And the shear strength is given as 40 MPa. So how will we go about this? What do we have to find first? So before going to what do we have to find, we have to go for a back calculation, say. So shear force, we have to determine the shear force ultimately. So shear force is shear strength multiplied by the shear area. So what is this shear area? Shear strength we know. So what is this shear area? What is shear area? Yeah, come on, please tell me. What is shear area? What is shear area? What is shear area? If you don't give me answer, how will I be able to understand? Huh? How will I be able to proceed? So this is the
Sir, we need to calculate phi.
yeah, we will be needing to calculate phi. But why phi? We have to arrive at that first, right? So what is the shear area? This is the shear area, right? Shear area is the width multiplied by the length of the shear plane. Am I correct?
Yes, sir.
And this angle is phi. So this is tau multiplied by W multiplied by what is Ls? Ls is equal to T naught by sine phi. So we do not know the value of phi. So that is why we need to know the value of phi. So we have the formula tan phi is equal to RC cos alpha, or just R, let me say. So this is R cos alpha by 1 minus R
R
sine
sin alpha.
alpha. We know the value of alpha. So what is R? R is the chip thickness ratio, T naught by Tc. So 5 by 8. This is equal to 0.625. So you put in the values here. So 0.625 cos of alpha is 10 degree. 1 minus 0.625 sine of 10 degree. Okay. So this value comes out to be 0.6904. So phi is equal to tan inverse of 0.6904, that is 34.62 degree. Okay, so phi is known. So now we just have to do this back calculation. The back calculation we have to just go forward with it. So what is the area of the shear plane? Is W multiplied by T naught by sine phi. Okay, so this is 5 multiplied by sorry, the width is 10 multiplied by uncut chip thickness is 5 divided by sine 34.62. So this is 88.07 millimeter square. And the shear force Fs will be tau multiplied by the shear area. Tau is given as 40 MPa. MPa is basically Newton per millimeter square, okay, multiplied by 88.07 millimeter square. So millimeter square and millimeter square are getting cancelled. So what we get here is 3522.8 Newton or 3.5 kilonewton. So the correct option is option number B. So this way we can find out the shear force. So this kind of numericals are pretty common in any exam. So you have to understand how to proceed. If we do not know what value to find out, do a back calculation and find out which value, which basic value we do not know. Then you proceed. Okay. So is it clear to everybody?
Yes, sir.
Okay. So another problem now. How does the specific power consumption vary with the increasing uncut chip thickness? So how does the
Please
specific power?
go slide number 13, sir.
Sorry.
Please go on slide number 13, please. Question number 13. Oh, sorry. Question number 14.
Yeah.
Question number 14, first slide.
Yeah. So what is the doubt in here?
Okay, sir, it's done.
Okay. So how does the specific power consumption vary with the uncut chip thickness?
Sir, option A decreases.
Yeah. So specific power consumption decreases. Why does it decrease with the increasing uncut chip thickness?
Sir, I have seen in the lecture there is a graph between
Yeah.
the relation of the power consumption and the uncut chip thickness length.
Yeah. But why does it this decrease? Why does the why does, like, you have seen this graph, right? Specific power consumption, and this is the uncut chip thickness. So the graph takes a form like this. But why is the graph taking a form like this? What is the reason? So can anybody tell me what is the reason for this? See, at this region, just give me some few answers. That is a definition of power consumed to the work done. What is this work done then? Power consumed to the work done. Power consumed and the rate of work done will only give power. So not necessarily that. So give me a few answers. So at this value, what is the so the uncut chip thickness is smaller or larger? Like it is a small value or large value at this point?
Sir, smaller.
Yeah. So for a particular value of the depth of cut, suppose sorry, for a particular removal we need, suppose this is the removal, this is the, suppose we have to remove till 5 mm. Okay, so suppose this is the value 5 mm, a high value. Okay, now in this case and this is a very low value, say 1 mm. So if we take instead in this 5 mm, instead of 5 mm, if we take a cut like this, 1 mm, okay, this is 1 mm, then to achieve a depth of 5 mm, how many cuts do we will have to make?
5.
Yeah, 5 cuts. So the necessarily we can assume that the shearing work, that is the shear work required for 1 mm, for this 1 mm thickness, uh, like for this 5 mm thickness, the shearing work required will be equal to 5 times that required for 1 mm. This is just we are assuming. But see, the chip area, this chip area, whatever is the chip area, is same as this chip area, because it does not depend on what depth of cut we are giving. It does depends that what is the W value. So the W value will be the same in both the cases, and this is basically the chip flow. Only the chip is flowing, so it has no relationship with the depth of cut. So this friction value will be the same in this friction value also. So for 5 curves, this friction value will be the with 1 mm depth of cut, the frictional work to be done will be 5 times, right, for this one cut required. Like for one cut, say the frictional work required is Fw. For this one also we require Fw. Therefore, since we need 5 cuts, so we need a total frictional work of 5 Fw. So this frictional work will be more. Okay, so if we take small cuts, then the total frictional work will be more. Even if the shearing work is same, the frictional work will be more, because we are cutting multiple number of times. That is why the since the frictional work is more, so the total work will be more, and hence the specific power consumption will be more for lower chip thickness. As the chip thickness decreases, suppose this is 2.5 mm, then we will need only 2 cuts. Then this will be only 2 times of the frictional work, so the specific power consumption will decrease, and this will keep on decreasing as we increase the uncut chip thickness. So the specific power consumption decreases with the uncut chip thickness. Have you understood this? Is it clear to everybody?
Yes, sir.
So any doubt in this? Any doubt? Okay. Now coming to the next problem, the break-in wear. Break-in wear refers to which of these? Any idea what is break-in wear? See, the rate of the wear varies, is not constant. What happens is, suppose we are taking the flank wear in millimeter here, and this is the time. Okay, so it will vary something like this. I hope you have seen this graph. Have you seen this graph in the lecture? See, this is the initial time in which the tool comes in contact with the workpiece. There is an increasing wear, but the rate of wear gradually decreases. This is the gradual wear, like it will keep on steady state wear. This is steady wear. The rate of wear is constant with time. This is accelerated wear. That is, the rate of wear is now increasing with time. See, the rate is increasing with time. The slope is increasing. So this will finally result in failure of tool. And this is basically the break-in wear. This happens when the tool comes in contact with the workpiece. See, the slope is decreasing here. So this is the wear rate is decreasing with time. Is decreasing with time. So these are the three like zones of wear with respect to time. Okay, so break in wear refers to the wear when the wear rate is decreasing with time. So is it clear to you?
Yes, sir.
Okay, so coming to the last problem for today. So as the cutting speed increases, the tool life varies as which of these?
Answer B.
Decreases, yeah. Increases and then remains constant. Why do you think it increases and then remains constant? See, there is a equation, Taylor's tool life equation, which is written as V t to the power n is constant. Okay, this is the cutting speed and this is the tool life in minute, and this is a constant value. Okay, so we can say that V is C by t to the power of n. So, or you can say T is C 1 upon n, V to the power 1 upon n. So T is inversely proportional to V to the power 1 upon n. So as V increases, T decreases.
Decreases.
Yeah. So the option is option number B. Okay. So I hope it is clear to everybody.
Just show me slide number 20.
Okay. This one,
2020.
20. Yeah.
Okay, sir.
Yeah. So the answer here will be decreases. Yeah. A. So is it clear to everybody? Uh, what have you written? With reference to the Taylor's equation, the percentage of tool life changes when the cutting speed is reduced to half.
Sir, can you explain this question?
Uh, what is this question? With reference to the Taylor's equation, the percentage of tool life changes when the cutting speed is reduced to half. N is 0.4 and C is 300. So what are you trying to find here? Uh, you have said that the cutting speed is reduced to half. So V t to the power of n is constant here. So let us denote V1 t1 to the power of n is V2 t to the power of n. So you have said that the cutting speed is reduced to half. So V2 is 0.5 of V1, right? So V1 by V2 is T1 by T2 to the power n. Sorry, T2 uh, V1 by V2 is T2 by T1 to the power n. So V1 by V2 is what? 2. This is T2 by T1 to the power of n. N you have given as 0.4. So the percentage of tool life increase. So T2 by T1 is equal to 2 to the power 1 by 0.4, right? So 1 by 0.4 is what? 2 to the power 2.5 or what? Or, yeah, 2.5. So what is 2 to the power 2.5? It is
Sir, 5.65.
5.65. So T2 will be 5.65 times of T1. So T2 minus T1 will be what? That is delta T is equal to what? 4.65. times of T1. So if we take the percentage increase, it will be like 465%.
Okay, sir.
Uh, but is it a question of your present assignment?
Yes, sir. Only that question I couldn't understand.
See, uh, we are not supposed, if you have not submitted the assignment yet, have you submitted the assignment yet?
Sir, I have submitted, but the deadline is tomorrow.
Okay. So what I am saying is that before submission or before the close of the deadline, you are not supposed to ask the questions, or we are not supposed to give solutions for the present assignment questions. Okay. So
Okay, sir.
let this be just an exception, but from the next time onwards, if you have any doubt for the present assignments, you can ask like in the next week after the deadline is over. Okay.
Okay, sir. Okay.
Yeah, or rather, if you have any doubt in the solution, because I am taking that even the solutions are being posted. So if you have any doubt in the solution, you can ask in the discussion forum also, so that the professor or the TA of the course in the institute itself can answer. Okay, so that's what I meant. Anyway, so thanks for joining. See you in the next class then.
Sir, please go on the slide of question number 9, sir. Actually, I have not, I could not noted that question.
Which one?
Question number 9, sir. Question number 9.
Question number 9. Okay. Yeah, this one.
Okay. And then question number 15, second slide, sir. Please. Question number 15, both slides actually. Question number 15 was in two slides.
Yeah,
Okay. Yeah, it's second part.
this does not have a second part.
Thank you.
Yeah. Okay. Yeah. Thanks. You may leave then. Thank you.